Welcome to the solving of question 2. So initially in this question, we're basically just extending what was taught in the first question. And right now, we're basically visualizing the C curve in three-dimensional space. So for the first question, 2a, we're trying to find the curve. We're trying to prove why writing the new curve C prime can be written as t squared plus t to the power 4. So basically how they derive this is pretty simple. The parameterization of the respective y and x components is t squared and t. So simply by plugging this into the z component, you get z is equal to t squared plus t squared squared, because that was the equation that was originally given to us here in question 1. So that will give you the z component. So once you get that, you get, as they stated before, t squared plus t to the power 4. So the second part, we literally just put a 0, and I'll just give a bit of explanation as to what's happening over here. So we're trying to project the curve onto the YZ plane. So we do this by basically just basically what we're trying to say here is that the parametric value of x is not really taken into account when we are just projecting this curve on one specific plane, which is the YZ plane. So C, we basically take it into function form, right? So here we have the fact that y is equal to t squared, and we're just basically taking z is equal to g of y, and we are trying to put that in terms of y. So since they said that y is equal to t squared, this is the original z expression, and we are taking that expression and just putting it in forms of y. So t squared is equal to y. T to the power 4 can also be written as t squared squared, so it's y squared. So that's how we derive g. And then finally, to find the area under this curve, double prime, c double prime, we should just integrate the expression. So dy is equal to 1, so we can put that there. But also the bounds have been determined because those were the bounds that were given to us in the first problem. And if you do the integration, then you eventually end up with this expression, which condenses to 5/6, solving this problem.
So for question 3 on worksheet 7, we're given a vector function f is equal to x squared plus y squared, comma x squared plus y squared. And we're given a curve which is stated it's the same as the one in question 1. So it's y equals x squared from 0, 0 to 1, 1. And we are asked to find this line integral. So the way we'd go about solving this, the first step would be to parameterize the curve. So if we set x equal to t, then based on this equation, y is equal to t squared. And then t would be in between 0 and 1. Okay, so the line integral for this problem is equivalent to the integral from a to b of f of r of t dot product r prime of t. So since we've already established that x is equal to t and y is equal to t squared, and we know that f is equal to x squared plus y squared, comma x squared plus y squared, we can substitute those values for t in, and we get f is equal to t squared plus t to the 4th, comma t squared plus t to the 4th. So from here, we want to find the r prime of t component. So we know that r of t is equal to x comma y. And again, if we substitute those values in for those values of x and y that we know, we get t comma t squared. And then to take the integral of that, or excuse me, the derivative, you just take the derivative of the x component and the y component. So you get r prime of t is equal to 1 comma 2t. So finally, you substitute those in, we get the integral from 0 to 1, and that's the parameters for t we set earlier on. So the dot product of t squared plus t to the 4th, comma t squared plus t to the 4th, and 1 comma 2t with respect to t. Okay, so given the following integral, the integral from 0 to 1 of the dot product of t squared plus t to the fourth, t squared plus t to the fourth, and then 1 comma 2t. The way we just take the dot product is we multiply the x components and add them to the product of the y components. So I chose to split these integrals up to demonstrate that they are in fact the same answer as the sum of 1b plus 1c. So the integral on the left, which would be multiplying the x components together, that integral is equivalent to the line integral of f of xy with respect to x. And the second part, the same could be said, it's just the integral with respect to y. Okay, so now finally to solve these two integrals that we have, we're just going to use basic integration techniques. So we'll start with the x component right here. So we have the integral from 1 to 0 of t squared plus t to the fourth. And then you just get, it's basic integration, you get 1/3 t to t cubed plus 1/5 t to the fifth. And since it's only 1 to 0, we can really just kind of substitute 1 in for here. And we get 1/3 plus 1/5, which is equal to 8 over 15. Then for the y component, we just distribute the 2t across to the t squared plus t to the fourth. So you get the integral from 0 to 1 of 2t cubed plus 2t to the fifth. And that is equivalent to 1/2 t to the fourth plus 1/3 t to the sixth. Again, since it's only 1 to 0, and there is a variable on both components, you can really just substitute 1 in, and we get 1/2 plus 1/3, and that's equal to 5 over 6. So finally, we just want to add these two numbers together. So 5/6 plus 8/15, you get a common denominator, so you get 25 over 30 plus 16 over 30. So your final answer is 41 over 30.
For A asks us to find the parameterization for the line from AB to point CD. So we're going to take the vector of AB, our first point, and add it to the distance between the second point from the first, which would be C minus A, and D minus B. Multiply that by T. Simplified. This is A plus T times C minus A, and B plus T times D minus B. And our bounds on T are between 0 and 1. B asks for a path from 1, 0 to 0, negative 1 along a circle of radius 1, the short way around. To parameterize circles, we use cosine and sine. However, if we do it this way with positive cosine and positive sine, this would be in the bounds of 0 and 2 pi, which doesn't work as it's not the short way around. This one is counterclockwise. As you can see, if you graph it, a rough sketch, these are our points 1, 0, 0, negative 1. From 0 to 2 pi goes around this way. So what we can do is have cosine of t and negative sine of t with our bounds between, instead, 0 and pi over 2. This gives us the quote-unquote short way around, going clockwise. C asks us for the intersection of x plus 2y plus 3z equals 6 and x squared plus y squared equals 16. If we want to look at it graphically, we know that there's radius of 4. And it goes up like this. And we can imagine sort of plane going through here, a rough sketch. We know, given our radius of 4 and that we're given the equation for a circle, we know that it is 4 cosine of t and 4 sine of t for x and y respectively. Now we look for z. To this we can take this equation and solve for z instead. So we have 3z equaling 6 minus x minus 2y, and then z equals 1/3 times 6 minus x minus 2y. We can take our 4 cosine of t and 4 sine of t and plug that in. Which makes it 4 cosine t for x and 8 sine of t for y, which gives us our final answer: 4 cosine t, 4 sine of t, and then what we found for z. Our parameters are simply between 0 and 2 pi.